Okay, so in this video, I'm going to show another way of solving problem F45. So F45 is a relatively simple problem. We did this in another video by hand, but it involved this integral. Okay, so this is a problem with a bar with a uniformly distributed load. And because you have a uniformly distributed load, the internal axial reaction force is a function of position. Since it's not constant, you can't use the PL over AE. So you actually have to do the integral. You have to integrate the strain to get the total elongation. And we showed that the mathematics of that last time. The difficulty is, solving for the integral. So it's not that hard. It's stuff you did as a freshman, but often we get a little rusty with doing integrals, and sometimes it gets scary. So using programs like Mathematica can make your life a lot easier. It makes the ability to solve problems with integrals, basically trivial. Okay. This is a simple integral. So let me start Mathematica. This is on a Mac, so it might look a little different if you do it on a PC. Mathematica is a really powerful tool. I encourage all engineering students that have access to Mathematica to get familiar with learning how to use Mathematica. All right. It has this nice little notebook environment that lets you easily perform lots of complicated mathematics, cool looking plots. It's a very powerful tool. There's lots of online help. So I can't give a full Mathematica thing, but I'll just show you how Mathematica makes solving this problem easy, and hopefully that'll motivate you to learn a little bit on your own. So the heart of Mathematica are these notebooks, okay? So here's a notebook. It's like a blank document, but you can put in mathematical statements that can evaluate it. So the big one we're going to do here is because we have this integral. It allows you to do stuff like, let's put in a integral. So let's integrate on the variable x, and let's just put in, 3x squared. Whoops. And we can put this whole thing over 1 minus x. So that's kind of a complicated integral, but you can evaluate this from 0 to 2, okay? So I type it in just as you would see it in a text, so that's relatively easy to do. You hit Shift Return, and it should numerically integrate this for you. Oh, it didn't like the integral. Okay. Well, maybe this is a bad integral for it to do. Let's make it a little simpler and see if it figures it out. Oh, it's because I should be careful. I have a singularity here, obviously, at x equal to 1. So let's go from 0 to 0.2. That's the problem. You see, when I had, I got a pole here at x equal to 1. That's what didn't converge. So here's the integral. It turns out to be complex. Okay. And that's what it is. All right. Let's try one that's more basic. That's what you can see. 3x squared minus 5. Okay. Why is it barking at me now? Yeah, there it goes. Once I put it in parentheses, okay? So there's the integral, okay? That's what it mathematically evaluates to. All right, the neat thing about doing notebooks, let's delete this, is that I can also define all the variables for the problem up front, and I don't have to worry about making silly calculator errors, because it's quite a powerful calculator as well. So let's define some of the variables. So the diameter is, let's do everything. You can actually do units in here, but let's do everything in terms of SI units. So the diameter is 0.02 meters. We're going to assume everything is in meters. What else do we have? We have the length, I'll call it capital L, is 0.9 meters. The The distributed force, let's call it W, is 30,000, and that's newtons per meter. Again, we'll do everything in SI just so I don't have to worry about unit conversions, because I don't write units easily in here. And what else do we need? We need Young's modulus. We'll call it Young, and that is 73.1 times 10 to the 9th pascals. Okay? So all those variables are now defined. Okay? Now I can do things like define the cross-sectional area, A. We know that's going to be pi. And Mathematica already understands that pi is evaluated as that over 4 times the diameter. The diameter, we can use the symbolic variable diameter, to the second. Okay? So that gives me the numerical valuation for the area. It's stored as the variable A now. And now I can get the integral formula. So delta, that's the elongation. That's defined as the integral from x equal to 0 to x equal L. The expression is, let's put that's the axial force. That's a function of x over A times Young dx. Okay, I won't be able to evaluate this because I actually have to define F, but we know what F is. Let me put it up a step higher. F equals, we did that from the force balance free body diagram from the previous video. So it is W times L minus X. Okay? So there's the evaluation of F, and now I should be able to do this. And it computes delta as this value, and that's the answer. Okay? You can clean it up a little bit. You can actually put it in text, and this is a F4, what was this, F4.5 in Hibbeler. Okay, so we could actually change the font to make it look, kind of cool. All right. And then you can put it in other notes. We could say we're going to first define the variables. Variable. Compute the cross sectional area. Compute the internal reaction force. And then find the elongation. So you can actually set it up like kind of as you would as a homework problem. And the nice thing about this is once you do it once, what am I doing? It doesn't do spell checking though. Okay. You can go through and we can say, well, what if the length is now, well, we can change another problem, or maybe the distributed force is a function of x. Okay? So now I put in here W. It's actually a function of x. So this is a linear distributed one, and now we can go through and reevaluate everything. Obviously the A is the same. Now the F is different. You see we have an x in front of it, and then when we do the elongation, it changes the value. So this solved the elongation for a linearly distributed force. You could put in other more complicated ones. What if it's a sinusoidal, right? So now it's has a sinusoidal distribution, okay? We can go through and reevaluate the axial force and then find the elongation, and it computes it for you automatically. So very powerful, and I highly recommend using it if you for doing homeworks. Unfortunately, it's difficult to do these things for quizzes, but I mean, it's really a very powerful tool. Okay, you can save it. There you go.